Here we are at our chapter 8, our logarithms. Now I mentioned in the past that chapter 7 and chapter 8 really do go together quite well, and chapter 7, you'll remember, was on exponents, and now we're doing logarithms. So I'll come back to that topic in about 20 seconds or so, but first I just want to remind ourselves about what inverse means. Okay, it says remember to find the inverse of a function, we switch the x and the y values and then solve for y. So if this is our initial function, let's say if we have y is equal to some base b to the power of x, that is an example of an exponential function, and we took some time learning how to graph and solve questions using that. The inverse of this is we'll switch the x and the y. Okay, so this is the inverse version. These are not the same functions. Another way of doing an inverse is, so that's the first way, the easiest way is to switch the x and y values. A second way to find the inverse is to reflect over the y equals x line. So if we were to graph this one is going to look different because it will be reflection. So it's not the same function, it's the inverse function. Okay, so looking at this, x is equal to b to the power of y. If we were to solve for y now and make it look kind of more normal, in order to solve for y, we have a problem because y is an exponent. So this is why logarithms were invented, was to exactly in this situation, how do we solve for y? So this is what we get. So we've introduced a new term in there, that log. Okay, so you can think of log as an inverse function of exponents. Okay, so if I have x equals b to the power of y, and if I have y is equal to log base b of x, these mean the same thing. Okay, so we can switch from exponential form, this is the exponential form of it, this is the logarithmic form of the exact same expression. So if we were to graph this or we were to graph that, it looks the same. Okay, so looking at this, b is the base of the log. Okay, base of the log, and that's easy to see because base is usually something that's on the bottom, and when you look over here, the base is on the bottom, like this y is higher than it, and over here the b is in subscript and it's also on the bottom. So this is kind of easy to identify, easiest to spot. Okay, so if I was to look over here, the base is 2. Right? It's the one that's lower. And in exponential form, here the base is 2. Right? So anytime you're going to look, the base is the one that's lower. Okay? Y, if you're looking over here, y is the exponent. So you can say it's the log or the answer. I usually think of it as the exponent. Okay, so the answer for logs, this y, is the exponent. And x is the argument. Okay, so it's a bit of a new term for us to call something the argument, but you're going to see that more if you continue on in math. So at least we have a name for it. We can sort of hang it on a word. We're going to call that the argument. Okay, so looking over here, it says sketch the graph of y is equal 2 to the power of x and its inverse. So y is equal 2 to the power of x. We can graph that. We know how to graph these types of things. So if we say y is equal to 2 to the power of x, and we're to do a bit of an x and y column, our easiest one is to make an x of 0. And 2 to the power of 0 is always equal to 1. So it's our kind of favorite place to start. If we put a 1 in for x, it's going to be 2 to the power of 1, so that's the same thing as 2. If we did a 3 in, oh, sorry, we shouldn't jump so high. Did a 2 in for x, then we'd have 2 to the power of 2, which is equal to 4. Just a little bit off of our scale, but I guess it would be over there, right? So here I'll even label this. This would be 0, 1. over here, this would be 1 comma 2. And up over here, kind of hidden away, this would be 2 comma 4. We could also go over here and we could put a negative 1 in. 2 to the power of negative 1 is equal to 1/2. So this would be over here. So this would be negative 1 comma 1/2. Okay, so that is our original function. Okay, now the inverse, better pick a different color. So the inverse, if we have y is equal to 2 to the power of x. Now the inverse is, switch the x and the y, it's x is equal to 2 to the power of y. So the easiest way to say, how do you graph the inverse? You take these x and y's and you just switch them. So instead of negative 1 comma half, we do the other way around. So I'm going to write my x here, my y. Instead of 0 comma 1, now I have 1 comma 0. And where does that go? 1 comma 0 is right there, our green one. Instead of 1 comma 2, now we're going to have 2 comma 1. So that would go right here. Instead of negative 1 comma half, I will have 1/2 comma negative 1. So 1/2 negative 1. And what was that last one? Instead of 2 comma 4, I will have 4 comma 2. So I'm just switching the x and the y's. 4, maybe over there, comma 2 would be about over there. Okay, so let's go back to blue and make our line look nicer. So our line, trying to make a nice curve here, kind of goes that way. And we do have an asymptote, a horizontal asymptote right there. So our other line, our green one, we can see a bit of that shape now. Will look like this. Okay, and remember that the other way of defining an inverse is to, I wrote it up somewhere up here, didn't I, is to reflect over the y is equal to x line. So maybe I'll do that one in red. So the y is equal to x line. Something like that. So here is our y is equal to x. So when x is 1, y is 1, and so on. So you can see how this reflection works. Here in my original function, this has a horizontal asymptote at y is equal to 0. And because of that reflection, this one will have a vertical asymptote at x equals 0. So we would have this line here approaches but never touches the vertical, the y-axis. Okay, so that's how you sketch the logs. Is you can sketch this and then do the inverse, switching the x and the y's. The equation of the log of the inverse is y is equal to log base 2 of x. So let's see, we had x is equal to 2 to the power of y. So just looking at the way this works, so if this is the exponential form, and the log form, the base is 2, you can see how it's lower, so I'd write log and write the 2 lower. And now these kind of switch sides in a way. This is the exponent, which is like the answer, and this x is the argument. So when I graph this, and I can say, okay, I guess I would write in blue, and I'd say here this is y is equal to 2 to the power of x. And in green, if I was to label this, I can either label it as x is equal to 2 to the power of y, but typically we don't write x equals when we're saying what that graph is. Better would be to write it in log form of y is equal to log base 2 of x. Right? So these are identical expressions or identical equations. All right, so let's go on to the next page here. And we have this is given to us in exponential form, and we want to switch it into logarithmic form. So the base is 4, so I'll take log put a 4 over there. Now n is the exponent, so that's my answer. All right, that, and m is the argument. So it simply looks like that. It doesn't say find what m and n are. It just says expressed in logarithmic form. So this is exponential form, and now here we are in logarithmic form. Okay, now this one we're supposed to switch the other way. They've given it to us in logarithmic form, and we should switch it to exponential form. Again, start with the base, so that's the 2. So that will be 2, and then to the power of, which is the exponent. Oh yeah, the answer is the exponent. So 2 to the power of 3 is equal to 8. Now I can write this 8 equals that way, or I could write 2 to the power of 3 is equal to 8. It doesn't really matter, does it? I guess this is more similar to our example number 2. Now we've switched from express to evaluate, so at the end of this question I should actually say x equals something. Alright, so the first step is I'm going to switch it to exponential form. To switch to exponential form, here's my base, the 2. Now x is the answer, so that's the exponent, so it's 2 to the power of x is equal to 16. So 2 to the power of x, 16 is also 2 to the power of 4, so therefore x is equal to 4. Excellent. We did it. We evaluated x is equal to 4. How about this one? So again, I'm going to switch to exponential form. So I will say that here's my base is 2, so it's 2 to the power of, well, there's no equal something, so I'm just going to add one. So I can say equals whatever. I like to say equals y. You can pick x, you can pick anything you want. So 2 to the power of y is equal to 1/4. Okay, so we really have to add some type of variable here in order to solve our question, because we need something to put in here before we can go through the motions of actually solving it. Okay, so just like in our previous question, we had 2 to the power of x is equal to 16. Here, if 2 to the power of y is equal to 1/4, we change 16 to some expression with a base 2. We can do the same thing here. We can say this is equal to 1 over 2 squared. So 2 to the power of y is equal to 2 to the negative 2. Okay, and then it's quite clear that y is equal to negative 2. I want you to note that in all these things, remember this is the base. Okay, maybe I'll switch to green here. This is the exponent. And maybe red here. This is, what do we call it? The argument, right? The only thing of these three things that is allowed to be negative is the exponent part, right? So we can have a 2 to the power of negative 2, and that works fine. Okay, if you go to the bottom here, the base can't be negative. Okay, and the argument is always positive. So in other words, as simply as you can write it here, the base and the argument I think there's an E in there, I'm not even sure. The base and the argument have to be positive. Okay, so here's an example where, and again I'll have to put an equals y. The argument is negative. Okay, so right away I know I'm going to get a no solution on this. But let's just walk through it and see why this is the case. 3 is the base, so putting in an exponential form, 3 to the, this is the exponent, y, is equal to negative 27. We had an example that was very similar when we did exponents, and it looks like it's possible. If I go 3 to the power of y is equal to negative, I can put 27 in terms of 3. It's 3 threes, 3 times 3 times 3. But there's no way that I can put in a value for y to make something negative. Like we might think, hey, what if I put 3 to the negative 3? Would that work? Well, no, it doesn't, because 3 to the power of negative 3 is 1 over 3 to the third. right? And 1 over 3/3 is 1 over 27, and that is not equal to negative 27. So no matter what kind of number I put in here for y, there's no way I'm going to get a negative. Okay, so that's sort of a verify method of proving that you cannot have an argument that's negative. So the correct way to answer that question would be to say no solution. Looking at example number 5, x is the base. So again, we're just going to put these things in exponential form. So say x to the power of 1/2 is equal to 5. And now x to the power of 1/2, remember how this works. This denominator 2 would be another way of looking at it as a root. So this would be the same thing as a square root. Don't have to put the 2 in there, but we'll just make it clear, is equal to 5. So if we were to solve for x, if we were to square both sides, I could get x is equal to positive 5, and I could get x is equal to negative 5. At this point, I should check both solutions out. I should go and put them back, substitute them over here. If I put a positive 5 in there, we're good to go because the base is positive. Remember, our base has to be positive, and so that would work. Boom, boom. But if I put the negative 5 in there, we would have no solution. So what you need to do is you need to demonstrate that you found this root. Okay, you found this solution, but then you rejected it. Okay, so this would be enough, or if you really want to do a good job, you could at this point say, x equals negative 5 is an extraneous root. Okay, so if you really want to look good, you can write something like that. But even just writing out x equals negative 5 and then crossing it out is good enough. Okay, looking at our next question here. Oh, well, we don't have any base here. So the other note, it says, when the base is not indicated, this means that there is a base of 10. It's kind of like the default for logs. Okay, so when you use the log button on your calculator, it's always log base 10, unless there might be some fancy calculators out there that will do logs with other bases, but otherwise, whenever you use the log button, it will be a base 10. So the first step would be to rewrite it like this. And now let's put it in exponential form. So this will be the base, 10 to the power of negative 3 is equal to x. And you might get a little nervous and say, whoa, Mr. Speiser, there's a negative here. We can't have negatives. Oh, but we can actually, because we're not allowed to have a negative base or a negative argument. Okay, so this 10 can't be negative, and this value for x can't be negative, but we can have a negative 3 here. And in fact, it kind of makes sense because we can actually solve this question. What is 10 to the power of negative 3? It's the same thing as 1 over 10 to the third power. So that would be equal to 1 over 1,000. And you can leave it in fractional form. If you really wanted to do tenths, hundredths, you could put it into decimal form if you wanted to. All right, how much more do we have here? I think we're getting close to the end of this page. Log base 16 of x is equal to 3/4. All right, so I will use 16 as my base. To the power of 3/4 is equal to x. Well, it looks a little funny here with this 3 over 4, but you remember how this works is that this is the root and this will be the power. So I could write this as 16 to the third power and then a fourth root of it, right? Or I could also write it 16, the fourth root of 16, and then cube it is equal to x. Okay, so this is just two different ways of putting the orders in different ways, and it does make sense to have it this way because I can actually figure out what the fourth root of 16 is. If you recall, 2 times 2 times 2 times 2, oops, I missed a 2 there, that's going to be equal to 16. So 2 to the fourth is equal to 16. So what is the fourth root? The fourth root of 2 to the fourth, this part here, the fourth root of 2 to the fourth is simply 2. So we have 2 cubed is equal to x. So my x is going to be equal to 8. All right. one more over here. Oh, this looks a little bit crazy. We kind of have nested logs. We have a log inside of a log here. So what we need to do is take care of the inside one first. Okay, so we're gonna stop and we'll say let y equal log base 3 of 81. So we're just going to deal with that inside one first. So changing this to exponential form, the base is 3, so 3, and this is the exponent, 3 to the power of y is equal to 81. So 3 to the power of y is equal to 81 is 9 times 9, so that's 4 3's altogether, so we get y is equal to 4. So we can rewrite this expression now. Log base 2, and now wherever I see this log base 3 of 81, I can put a 4 in for it. And now putting this in exponential form, I get, here's my base of 2 to the power of x is equal to 4. So 2 to the x is equal to 2 squared, so x is equal to 2. And that's my final answer. Kinda cool. Now we have some estimate questions. So these would be, I guess, without any calculators at this point.
Good afternoon, students here. Afternoon.
Alright, so for these estimate the following volumes, we're going to try to do them without our calculators. So again, we're going to have to say equals y. So putting it in exponential form, we get 2 to the power of y is equal to 30. And here's where I have to go and say, oh, how do these powers of 2 work? 2 to the power of 3 is equal to 8. 2 to the power of 4 is equal to 16. 2 to the power of 5 is equal to 32. And now we need to do some estimation, okay? And it's going to be very close to 5. So I think a 4.9 would be a good estimate for that one. So something very close to 5. How about the log of 20? So there's two things we need to do. First of all, it's the default log of 10, since nothing was written, and we need to put a y there, and now convert to exponential form. So 10 to the power of y is equal to 20. So if 10 to the power of 1 is equal to 10, and 10 to the power of 2 is equal to 100, really it's going to be very, very close to 1. So you can do your own estimate. I think it works about closest to 1.3, but anything like 1.1 would be just fine. Very quickly, our last one here, log base 5 of 120. So if I put an exponential form, I get 5 to the power of y is equal to 120. And if you recall, 5 squared is 25. 5 cubed is equal to 125. So I want something that's very, very close to 3. So probably 2.9 would be pretty good. Actually, when I check it into my calculator, I think the answer is very, very close to, it's like 2.9875 or something like that. It's very, very, it's actually closer to 3 than it is to 2.9. But that'll work just well for you. Okay, so here's your homework on the bottom, and I look forward to seeing you in class.